All right, so this Pythagorean theorem basically is a way to get the magnitude given the components, right? So let's just remember this is the magnitude. These two things are called the components. All right, so we can get the magnitude if we know the components. All right, what else can we get? So a lot of times we're going to, a vector is magnitude and direction. So the other thing we're interested in is the direction. So when we talk about the direction, we're going to talk about this angle, again, in standard position. The angle back to the positive x-axis is what we usually refer to as the direction. There are other ways to do it. So this theta, what I'll call that is, I'm just going to write the direction of the vector v. Now that's a made-up symbol. That's people are usually just going to use theta, but the direction of vector v, I'm going to use this abbreviation for the direction of vector v. So if you look at this angle right here, so what we know is that let's put vx and v y on here. So if this is Vy, let's get a little bit cluttered here, but this is Vx. All right, then how am I going to get a handle on this angle is the question that I'm dealing with right now. All right, well, I know that the tangent of theta is equal to this y over this x, right? It's equal, tangent of theta is like, if we call these r, x and y, tangent of theta is y over x. So in this case, it's Vy over Vx. So that means that theta is equal to the inverse tangent of Vy over Vx. So that's our next formula that we have here. It's equal to the inverse tangent of Vy over Vx. Okay, but you have to be careful because when we go from tangent to inverse tangent, tangent has a restricted domain. So that means that the inverse tangent you're going to get out of that is only ever going to be between negative pi over 2 and pi over 2 radians. But sometimes we want to say that the theta is over here, so we want to say that the theta is greater than pi over 2. So with the proviso here that you need to look at the quadrant, so look at quadrant to determine theta. And we'll see examples of this. Now here's another fun thing. In vector world, because it comes from physics, theta is often expressed in degrees because it comes from physics and engineering. All right, so this is the rare time that in calculus class you're going to sometimes need to put your calculator into degree mode, and you're going to have to be aware of whether you're in degrees or radians. So a lot of times we're going to express that theta in degrees. Okay, what else can we say? Basically what these are about is if I have the components, okay, I can get the magnitude and the direction. Right? What if I have the magnitude and the direction? Can I get the components? Answer, yes. So again, just using the trigonometry, I won't belabor this too much. It should be fairly clear that the x component of the vector is equal to the magnitude of the vector times cosine theta. That's just basic trig. All right, and so you can figure that out. If you're confused about it, let me know, but this is all you have to know. And Vy is the magnitude of the vector times sine of theta. All right, so these four formulas basically allow you to go from the components to the magnitude and the direction, from the magnitude and the direction to the components. All right, so I gave you a couple of homework assignments doing things like that, and let's see. I think we're going to look at one now, if I can interpret my notes. Oh yeah, so let's look at, so all of this is in 10.3 of your book. 10.3. So I'm going to look at page 545. And let's just start by looking at number 8 on page 545. So the question says, find the magnitude and the direction. Find magnitude and direction. And the problem specifies 0 degrees is less than or equal to theta is less than 360 degrees. So they want that direction in degrees in standard position. All right, so in fact, they say the angle theta that it forms with the positive axis, right? That's the same as the direction in standard position. So I'm going to be thinking, I have like this and wherever my vector points. Well, we'll look at it when we get it. So number 8 gives you negative 2 square root 3. So I have negative 2 square root 3. Now, by the way, here's something I failed to mention earlier. We use these cornery brackets to represent a vector. There are other ways to do it, but that's one of the most common ways. Have I already done that? I think I've done that somewhere. No, I haven't done that before. Okay, so now you know. We represent a vector with these cornery brackets because it's not a point. It's not a point in space. Look, points in space, you cannot add and multiply them because they're just points in space. Vectors are entities on which you can do operations, such as addition, multiplication, derivative. You can't do the derivative of a point, but you can do the derivative of a vector, a vector function. That's what we're going to be headed towards very soon. All right, so this is your Vx, and this is your Vy. All right, so first of all, finding the magnitude is easy. Let's give this vector a name. I'll cleverly call it V. So the magnitude of the vector V is equal to the square root of negative 2 squared plus negative 2 squared root 3 squared. I mean, I hardly have to write this out for you. You can figure it out. It's square root of, what is that going to be, 4 plus 12, right? So it's square root 16, so it's 4. All right, so the magnitude of the vector is 4. All right, what else can we say about this vector? So now we're going to look at the direction. So the direction of the vector v is equal to inverse tangent vy over vx, but we're going to have to be concern ourselves with the quadrant that we're in. We'll see what that looks like in a minute. So we need to go to our mode and go into degree mode because it wanted degrees, but then we're not going to forget that we're in degree mode when we do something else. All right, so quit out of there. I need inverse tangent of, let's see, I guess I'll do this. I won't use the fraction-y thingy. I'll just go negative 2 divided by parentheses negative 2 square root 3 out, close parentheses, that's going to work. All right, enter, and I get 30, okay? So it's 30 degrees, okay, equals 30 degrees. All right, but let's look at where this vector is. This vector is in the third quadrant, has a length of 4, and it's giving me a tangent, an inverse tangent that's 30 degrees. That means if it were in quadrant 1, it would be 30 degrees, but it's not. It's in quadrant 3, so it's going this way, and this is 30 degrees, and the length of it is 4. All right, so what's the real angle? The real angle is 180 plus 30 degrees, because we always take our angle, our direction, that's going to be angle to positive x-axis. All right, that's what that direction is always going to mean for us. So that's going to be 180 plus 30, which is 210 degrees. All right. So I'm not sure how to amend this properly because the direction isn't really 30 degrees. I guess we'll go like this. But it's not really 30 degrees. It's 210 degrees. There's probably a nicer way to write that. Because what we got, this 30 degrees is what you call that the reference angle. 30 degrees is the reference angle. But we have to look at the quadrants to find out what the real angle is, okay? So there's some basic operations on vectors. I think we'll do like 1 or 2 more of those, and then we'll start looking at calculus in these vectors because we haven't done any calculus yet. This is all just pre-calculus in physics.